Every day, ammonia helps feed nearly half the world's population. But making and processing ammonia requires enormous amounts of energy. What if we could do it more efficiently? Today, most ammonia is produced using the Haber-Bosch process, an industrial breakthrough that transformed agriculture and helped support billions of people worldwide. But that impact comes at a cost. The Haber-Bosch process relies on extremely high temperatures and pressures, making ammonia production one of the most energy-intensive chemical manufacturing processes used today. Researchers are exploring new ways to recover ammonia more efficiently. That's where my team comes in. My lab develops high-temperature ammonia-selective membranes. They allow ammonia to pass through while blocking other gases. If successful, these membrane systems could improve ammonia separation processes and industrial efficiency. However, there's one critical challenge in our way. How do we make these membranes survive real operating conditions? The membrane material we study is zinc chloride, which has a strong ammonia affinity, creating the potential for a simpler and lower-cost ammonia collection. But promising materials don't automatically become practical technologies. Zinc chloride presents a major challenge. It's hygroscopic, meaning it readily interacts with moisture, and at elevated temperatures it can lose mass over time. And if the membrane material slowly disappears or redistributes itself during operation, membrane performance suffers. Before we can improve separation performance, we first have to understand stability. My work began by using a sonication-assisted wet impregnation process to deposit zinc chloride onto stainless steel. I explored multiple preparation approaches with one goal. Can we build a membrane that performs better and lasts longer? This alternative deposition approach ultimately didn't outperform our lab's original method, but that result still mattered, because progress doesn't just come from discovering what works, it also comes from understanding what doesn't. Next, I used thermogravimetric analysis to understand how these membranes degrade over time. By exposing samples up to 300 degrees for 900 minutes, I measured how mass changed during operation. Through this work, we established reproducible methods and identified trends between thermal conditions and membrane stability. But TGA only tells part of the story. It happens at a very small scale. Industrial systems are far more complex, so now I'm developing a new experimental system to better bridge that gap. This system exposes molten zinc chloride to heated gas flow in both inert and ammonia environments, allowing us to study erosion and salt migration under elevated temperature conditions more representative of industrial operation, because understanding how materials fail is often the key to making them succeed. Membrane science and engineering isn't just about discovering promising materials. It's about building materials that can survive the environments where they matter most, because technologies only change the world if they can survive long enough to be used in it.